Okay, so this is 11.6, number 10, and so we have consider a function f of x y at 0.61. I'm going to copy this down. So in the direction of 7, 1, it has a directional derivative of 4 over rad 50. Let me give you a second to copy that down, and it's going to be 4 over rad 40 in the direction of 6, 2. These are vectors. The gradient of f, so we want to find the gradient. So obviously we don't know what that is. So all right, so let's take a look at that one. I'm going to stop the share. I'm going to go to my overhead and let's make that larger. Okay. So first of all, whenever you're doing directional derivatives, you got to convert these into unit vectors. So this will be rad square root 49 plus 1, so square root 50. So it'll be 7 over rad 50, 1 over rad 50. This will be 36 plus 4 is 40, so over square root 40, so 6 over square root 40, 2 over square root 40. Okay, so that's what we need to use for our directional derivatives. So the directional derivative formula is to take the gradient and then dot it with the actual vector that you're going into the direction of. Well, clearly we don't know what the gradient is. So I'll tell you what I use question marks. How about we'll just use A and B? Okay. So whatever the gradient is, we'll just call it A and B for now. So I have A and B. Now let's do it for the first one. It's going to be 7 over rad 50, 1 over rad 50. And that gives us 4 over rad 50 from here. And I'll do the same thing down here. I'm going to do the directional derivative with this vector, and it'll be AB dot, and then these two guys, 6 over rad 40, 2 over rad 40. And that's supposed to all equal 4 over rad 40. Okay, now let's actually perform the dot product. So this one I'll do right here. The first one, it's going to be 7 over rad 50 A plus 1 over rad 50 B equals 4 over rad 50. That's this one here. Now this one then follows, what we've got there, 6 over rad 40 A plus 2 over rad 40 B equals 4 over rad 40. Now this looks messy, but it's actually going to clean up real nice. But before I proceed, is there any questions with so far what I've said, what I've done? Okay. Oh, you can always just jump in if you need to. This is a system in two variables, two unknowns, A and B. And the rad 50, I can actually multiply the top row by rad 50 just to get rid of them, and the bottom row by rad 40. So I'll do that. Suddenly it cleans up real nice. It's 7A plus 1B equals 4. And on the bottom row, we have 6A plus 2B equals 4. And then that's just a system that we just got to solve. And I don't really care how you solve the system. If you got about 6 or 7 ways you can do it, I'll do the top where I multiply the top by -2. And by doing so, just kind of come down here now. It becomes -14A take away 2B equals -8. The bottom is 6A. It doesn't change actually. 6A plus 2B equals 4. But when I add them, the B's cancel. You get -4 on the right, and on the left, I get -8A. So it looks like A is 1/2. Okay, And then I can just go back and substitute to get b. So if I put it in right here, that would be a 3. So 6 times a half is 3. Subtract it out gives you a 1. And then it looks like divide by 2 and you get b is 1/2 as well. Now I should check that up here too. Let's make sure. So that would be 7 times a half. That's 7 halves. Plus 1/2 is 8 halves. Yep, that's 4. So that looks good. So that would be your gradient. So the gradient of f at this point is this vector. Okay. Does that help? Any questions on this one? Alrighty.
Get the format
Okay.
of it to enter,
Yeah.
but on the y, can you change it to 2 plus sine of 4t or something instead of just sine t?
Let's
Because
take a
when I
let's
did,
take a
oh, sorry.
let's take a look at it. Yeah, this one's got a lot going on. So this is, can you guys see that okay? It's 11.5, number 1. Let me copy down the main information here. We've got a function w equals x over y plus y over z. Meanwhile, x is equal to e to the 5t, y is equal to 2 plus sine t, and z is 2 plus cos 5t. Okay, we want to find the chain rule to find dw dt as functions of x, y, z, and t. We don't want to do any rewriting. Okay, and then from part 1, we want to evaluate when t is 0. So probably part 1 is the big one, right? So I'm going to stop the share, go to my overhead. All right. Um, we want to find dw dt. That means we have to find dw dx. So it's basically dw dx dt plus dw dy dt plus dw dz dt. Okay, that's the chain rule all spread out. And I realize I'm using this dot symbol. It's not a dot product. That's actually just multiplication, but it looks a little funny sticking the fractions together without something between them. So let's just see what we get. I'll just kind of work this out and let's just see where we go with it. So dw dx, that'll be 1 over y, and then that just drops out. So that's nice. And then dx dt, well, that's the derivative of this guy. So it's going to be 5 e to the 5t. dw dy, all right, that one's a little complicated. Y is in the denominator. I'm going to use that old trick that the derivative of 1 over y is negative 1 over y squared. Just like that. And then this will just be plus 1 over z. And then the derivative of this guy will be cosine t, so dy dt. And then derivative w dz, well, that's not anything. That'll be negative y over z squared. And then the derivative here will be negative sine 5t and then a 5. So negative 5 sine 5t. And I'm going to stop right there. I'm not going to do anything else to that. Now, your question might be ever so slightly different from mine because sometimes the coefficients are chosen randomly. But does that look similar to what you have up to possible coefficient differences?
Yes, everything looked similar.
Now, which part are you messing up or does it tell you?
No, I tried entering it like 7 different times in different formats, and it just didn't ever accept the answer. I don't know. It was something in the actual affinity that is not accepting it. But I did a practice one, and it was just the basic with just a sine t like you're doing here, and I was able to get that one and it entered properly. But when you did like a sine 4t in your y, it wasn't taking it for some reason.
I would have to look at your specific case, and the only thing I would be able to see is what you most recently entered. So it, it could be syntax. One thing you might try when you're entering like cosine t is put parentheses around the t. So maybe kind of tuck an extra set of parentheses like that. You see what I just did there?
Yep.
Just you got to remember the computers are, these systems are smart, but they're stupid. They take exactly what you enter and nothing more. And I've noticed sometimes they do stumble on syntax, and sometimes I'll see students type in like cost, like the word cost. They don't put a space in there, and it doesn't accept it. And so I have found that sometimes you just need to be super, almost really, really picky with these systems to get them to accept. I'll take a look at yours after this recording after the session is over, and see if I can't figure it out. But again, I'm only going to be able to see what you typed in last. So, but the common mistakes, maybe leaving off parentheses, maybe just forgetting a negative sign, something little like that. Could be just about anything.
Okay.
But
Nope.
in general, does that make sense what we did there?
Yes, yes, this makes sense.
I won't do the second part, but I'll just verbalize it. They wanted us to figure out the value when t is 0. Well, clearly, when you pop in 0, well, cosine of 0 is just 1. That'll just drop out the whole thing. A sine of 0 is 0, so this whole third part will just go away. E to the 0 will be 1, so that'll be a 5. Now, for x, y, and z that you have to figure out, you have to do those calculations here. Okay, I have a feeling you're going to get a lot of zeros, but so it should actually clean up pretty easily. All right. All right. 11.6, number 15. Here it is. Use the contour diagram of f in the figure below to decide if the specified directional derivatives will are positive, negative, or 0. All right, let's kind of make sense of this picture here. Can you guys see my cursor there when I do that?
Yes.
Okay. It looks like we're looking at a bowl-shaped surface because it looks like the contours are counting up as we go away from the center.
Yep.
So that'll help us. So this is like some parabolic bowl, we'll think. So at the point -2, 2, so that'll be roughly right where my finger there is. That's -2 and 2. And I want to go in the direction of negative I. Well, that's -1. So I is the x direction, j is the y direction. So I'm here and I go left, am I going up or down?
You're going up on the contours, so that would lead
Yeah,
it to
so
be
that'll be
positive.
that'll be positive. At 0, -2, that'll be here. Okay, and now I'm going negative j, so I'm going this way. So watch my finger. I'm here and I'm going this way. Am I going up or down?
Down, and it would be positive. It's increasing again.
So yes, you're going up. The z's are going up. Very good. At -1, 1, let's see, that'll be right here. And we're going in the direction of I plus j. So that's actually going to be a 45-degree angle. It's going to be going like this.
Yep.
Okay, so I'll give you a little hint. Anytime that the direction of the derivative is tangential to the contour, not orthogonal, but tangential. Does that make sense?
Yes, it does.
You're gonna get a zero derivative
Okay.
because the way to think about it is that let's say you're standing right here. You're standing inside this bowl somehow,
Right.
and you're gonna make a little tiny step in that direction. You're actually gonna stay level. So your direction, your
Okay.
change
So
in
think
z will
smaller
be zero.
scale because I've been thinking bigger scale and it's going and an increase in contour still if you keep going.
Right.
Um, but I think smaller and that'll be a more appropriate answer. Okay.
Yes. Well, and when you think about it, the derivative is always at a point. It's always, if you think of the Calc 1 equivalent, you're always looking at the tangent line to a curve, right? So the tangent line itself can extend forever, but we only care about the part that nicks the curve. And
Okay.
that's kind of what's going on here. So anytime your directional anytime the direction of your derivative is tangent to the contour, you're going to have a zero slope. So the part C should be zero.
Okay.
Let's take a look at a couple more. Negative 1, 1, so that's the same point. Now I'm going negative I plus j, so that's actually going to be going back 1 and up 1. That's actually going to be going orthogonal to the contour. This will be going up.
Yeah. So that'll be positive.
Yeah, and then I'm wondering, since we got them going, let's just do the last two. It's 0, negative 2, so I'm down here, 0, negative 2. I'm going to be going in the direction of I plus 2j. So I plus 2j would actually be pointing this direction. So watch my finger there. It's going to go that way. So it's not tangent to the curve. Is it going down?
Yeah, that'd be negative.
Yeah. And then it looks like same point, but this time we're going I minus 2j. So it's going to be going 1 over and down 2. So you're going to be going yay, like
Okay.
that.
Okay.
That should be up. Does that help?
Yes, it does.
There's not really much to show mathematically. This is one of those, just look at the picture. I think part C, though, is probably the trickiest one. Anything tangent
Yeah.
will have a zero slope. Here, the gradient is it's a vector form of your two partial derivatives. Okay, fair enough. Its geometrical significance is it points in the direction of max increase. Okay, so the gradient itself, once you plug in the point, so you plug in your actual x and y, it actually gives you a vector, and that points you in the direction of max increase. I think most people are comfortable with that. The actual slope is the magnitude. Okay, and this is a common mistake. I saw this occur in ed discussions. You do not reduce or alter the gradient values. Okay, because you get this kind of frustrating situation where it actually still points in the right direction. So you still get the correct answer. You'll still be counted as correct. But the slope value will be wrong if you reduce it. Because I've noticed sometimes you'll get a case where the gradient is like 10 and 20. So let's say you work out a question and you take the gradient and you plug in your values, blah, 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 and you get 10 and 20. Okay. That's the direction of max increase for this particular function, okay, at that whatever point you're at. All right, now it's tempting to want to factor out a 10 and just choose 1 and 2. It's even also tempting to want to make this into a unit vector. You don't want to do that. For the gradients, just leave them alone. Whatever you get for the gradient, leave it alone. So so this is correct. Now, notice if I do the magnitude, I have to keep the 10 and the 20 alive. I can't change those. So I get square root 500. That is the answer. That would be the actual slope. Now it's tempting, let's say, so what if I reduce this? Suppose I just say that it looks like 1 and 2. Okay. Well, you know what? You'll still get credit for correct direction because 1 and 2 points in the direction of 10 and 20. So these are actually parallel vectors. So as far as answering the question of what direction is the max slope, that's correct. But when you plug this into when you plug it into the magnitude formula, in this case, you just get rad 5. That's not correct. Okay. You need to keep the original values alive. So don't fall for any temptation to reduce. So I wanted to mention that. That's a common mistake.